Good morning and welcome to the enclosure on this lovely November morning. Unbelievably warm today, totally blue sky. Not what we typically expect for the Pacific Northwest in winter. Anyway, I am coming to you via a brand new high definition camera. It's my hope that this will greatly improve the quality of the videos I create and also make it easier to create those videos. Because up until now I've basically been doing it with the cell phone. And if this becomes easy enough for me to do, hopefully the end result is that you will see much more frequent updates from me during the build, where I can just do a quick video and explain what has happened of late, as opposed to sitting down late at night and typing out a 3 or 4 hour update on the blog. So hopefully you're going to enjoy these. I thought for our first video, Mr. Crow, our first video we would cover the details of my building envelope, right from the very first component that went in, which was the footing bags, to the latest component that I put in, which is the upper floor ceiling air barrier. So without further ado, let's get going and start showing you the details of what makes this the enclosure. Okay. As I obviously didn't have this camera during the build, I'm going to start by referring to a series of photos and describing the barriers. So altogether we've got a water barrier, which is the exterior surface that is the primary rain shedding surface. So that would be your roof surface and your cladding. Next we have what's called the WRB, which is the water resistant barrier. That is the most inward surface on an assembly that is allowed to get wet. So on the roof, it's typically the roofing or sometimes the membrane below the roofing. On walls, it is typically a type of sheathing membrane. So it's what goes over the plywood and underneath the cladding. Then we have our thermal barrier, which is what prevents heat from going out, cold from coming in, or vice versa, depending on the seasons. It prevents the movement of temperature through an assembly. And then finally, we have both an air and a vapor barrier. So the problem with the air and vapor barrier is that they have typically been combined in building code for decades. And a really good vapor barrier is a poly sheet. It's a class 1 vapor barrier. It allows virtually no vapor transfusion through it. But it is very, very, very difficult, if not impossible, to seal poly in a lasting way as an air barrier. Yes, you might be able to get through your air tightness test at construction, but if you come back 5 years, I would bet the farm that it will no longer be anywhere near the air tightness that it was at that time of construction. And that's even if you do pass at time of construction, because it's so difficult to seal around all of the penetrations within the home. So a better process is to define all of the barriers individually and then decide on where each one should go and whether or not they should be combined. And that is definitely the case with the air and the vapor barrier. If you remove the air barrier component from the vapor barrier, now you do not need what's called a class 1 vapor barrier. In our climate, you most likely only need a class 3 vapor barrier. And I'll describe this a little bit later on. But the barrier is basically keeping humidity, moisture within the interior air from diffusing to the wall assembly, to inside the wall assembly. The air barrier, on the other hand, can be anywhere within the assembly, and as long as it's continuous, will prevent the air movement through the assembly. So it can be on the inside surface, it can be in the middle, it can be on the outside surface. As long as it's continuous, it will prevent air movement through the assembly. So let's start the process by discussing the very first component installed on the build. As you see here, these are bag footings. They're a product called Fast Foot, which is a polyethylene fabric, and they were what I used to form the footings below the foundation. The intent of this product was to provide both an air and watertight barrier around the footing, which obviously contributes to the air barrier, but also prevents rising damp, which is the process by which unprotected footings sitting in water or on damp soil draw that water up by capillary action into the foundation, thereby wetting up the assembly and increasing the humidity within the home, moisture within the wall assembly, and too often there's a poly class 1 vapor barrier in the basement. Now you end up with moisture within the assembly that has no way to get out. For multiple reasons, I would recommend against using this product, and if I was doing this again, I would instead form the traditional footings and install a membrane on top of the wet concrete, as you see here, pressed in with the keyway. This is a Delta footing barrier provided by Dorkin. Just make sure that the footing barrier membrane is wide enough so that you can easily seal it to the sub-slab membrane and the foundation waterproofing membrane that will be installed at a later date. In this image, you can see the bagged footings installed around the outside perimeter for the exterior foundation walls. They were clamped to the first course of Nexem ICF forms that were used on this build. For the internal footings, I was able to convince my engineer to allow me to encapsulate these lower loaded footings with a high density XPS. I used Owens Corning Foamular 600, which is rated at 60 psi compression, and their Foamular 200, which is a 20 psi for the footing sides that don't see any compressive load. This provided a thermal break between the footings and the ground below the slab, increasing the R value of the assembly. And these stay-in-place footings then also were lined with a vapor barrier grade of poly and sealed to provide the air barrier, obviously, as well as the vapor and water barrier. And you can see all the red tape, which was used for air sealing. Again, if I was doing this again, this was 5+ years ago when I started this, I would have used a heavier grade poly and a better grade of tape than the red tape here. I do believe because it was so well supported and the concrete was pressing down on the tape, that the tape probably would hold in this situation. But if I was doing it in the future, I would give myself an extra level of protection. In this image, you can see how the plumbing penetrations were also detailed with my favorite R-guard. In this case, it was joint in seam, I believe, liquid flashing. Once the foundation was poured, we then proceeded with the exterior waterproofing and air barrier on the foundation wall. This image shows the installation of Supreme's Flamstick transition membrane between the bag footing and the torch-on membrane that would be installed later on the foundation wall surface. This is a peel and stick membrane on the back side that allows you to attach it to membranes that cannot see a hot flame. And then on the top surface is a surface that accepts a torch-on membrane. If you look closely right at the top margin of the membrane, you will see a reddish primer that was first rolled on the ICF block in the bag footings to accept the peel and stick membrane. With the transition membrane installed, we then were ready to install the main foundation membrane. I've never been a fan of the spray-on goop used in the majority of home construction in past years. During my home inspection career, I saw how poorly it performed. It's a very, very thin layer. It's often not straddling or bridging cracks that are in the foundation or any type of cold joints in the foundation. And then any amount of abrasion from things like backfilling will just wipe it away typically. I wanted something durable that would be 100% waterproof and also provide a lasting air barrier. It's crucial that this is a class 1 vapor barrier and 100% vapor closed to prevent wet up from the humid soil into your foundation. Your soil is always going to be 100%, so the moisture movement direction is always into the house. This is why you do not want to use a class 1 vapor barrier, i.e. poly, on your foundation walls on the inside surface. In our case, we used Supreme's torch and stick. The first step was to prime the walls, as you see here, with the black Elastical 500 primer. This bitumen-based primer allows for the bonding of the torch-on membrane that is installed in the next step. The main membrane started at the transition membrane down at the footing level and extended all the way to the top of the foundation wall, which extended 6 inches above grade as required by code. All penetrations through the membrane were carefully detailed to provide a water and airtight interface. My preferred detailing sealant is R-Guard Joint and Seam, the pink that you see here in the photo, and is from Prosoco. It sticks well to just about everything, is easy to install, and has a very high elasticity rating. Meaning in this case, this PVC pipe, as it expands and contracts due to temperature changes, the sealant will stretch out or compress as required to ensure an air and watertight joint. It does have a little bit of permeability, so I would not recommend this in a location where there could be sitting water, a horizontal surface like a windowsill, but for vertical surfaces it works great. In this image you can also see the start of the exterior thermal barrier being installed. We used 3 inches of Rockwool's Comfort Board IS, a semi-rigid panel of mineral wool. We increased the thickness of the insulation near the top of the wall to match with the greater temperature drops that will be seen above grade compared to below grade. This was accommodated by the steps you see visible in this foundation wall image. Next, we capped the assembly off with Delta Drain 6000 High-X dimple membrane that was installed outboard of the mineral wool insulation. The dimple sheet is placed with the dimples facing outward so that they do not dig into the insulation. Outboard of the Delta Drain, we installed a column of gravel to provide an additional drainage plane. This was then capped with Nylex 4551 non-woven polypropylene geotextile before the backfill was added and compacted in 6 to 8 inch lifts. The plywood you see with cleats in this photo is what we used to separate the gravel and the backfilled soil and was raised in lifts with a jack or a tractor. This ended up being an extremely time-consuming process, and I can fully understand why on most builds the backfill is not compacted and just basically thrown up against the wall with an excavator. Above grade, the barrier changed to a vapor permeable but waterproof membrane that was also airtight. We used the Delta Vent SA that you see here. This was a wonderful product to apply and was easy even for one person to install in long sheets. The membrane has an awesome 31 perm rating, meaning that any moisture that builds up in the assembly from say a small water leak or a plumbing leak can easily dry to the outdoors. Unlike OSB, plywood also becomes more vapor open as it wets up, providing an additional durability and level of safety to the assembly. The Delta Vent SA membrane overlaps and is sealed to the foundation torchon membrane to provide continuity in the water shedding surface, but more importantly, a continuous uninterrupted air barrier. This is done with the multi-band tape that you can see right here, sealed to both the foundation membrane and then the Delta Vent membrane above. This is also used to seal any vertical seams as well as any horizontal seams that are made with cut fabric. The horizontal seams that are factory edge, as you see here, this has a backup glue joint between basically these two locations that provides an additional mechanical adhesion between the lapping surfaces. I'm firmly in the camp that the only logical place to install an air barrier is on the exterior of the sheathing. This is an easy install as you're already putting on a WRB at this location, so just by changing the product and taping the seams, you have an awesome airtight assembly. You're also now dealing with just large square penetrations like windows and doors, compared to the hundreds, if not thousands, of penetrations you can see in the average home on the inside surfaces when you take into account things like cable vision, electrical outlets, light switches, ceiling lights, all that kind of stuff. Also, with an exterior air barrier, sealing around the rim boards becomes moot. You just continue the membrane up past that assembly and ignore it. You don't have to have lapped membranes that go over the top plates of one floor and around the rim boards and then under the top plates of the floor above. As the exterior membrane was installed, the few penetrations that we did have were sealed with the R-guard joint and seam. And if you got really close eyes, you'll notice that the tape has not been yet installed along this location. This is in the garage where I'm sealing the inside walls that are common to the house to a torchon membrane that was torched to the garage floor to provide the continuity of air barrier. And the Delta multi-band tape still has to be applied along that seam. You can also see here I have 6 inches of exterior mineral wool insulation. This is becoming best practice as we increase our levels of insulation. We need to place that insulation outboard of the sheathing to allow the sheathing to stay warm enough that it prevents a dew point temperature from occurring. And by placing this insulation on the outboard side of the sheathing membrane air and water barrier, we now provide a level of protection to that membrane, ensuring that it has decades of trouble-free operation in the future. Repeating what I said earlier, remember that the air barrier can be anywhere in the assembly. As long as it is continuous, it will prevent the movement of air through that assembly. We continue our barriers now at the very top of the wall assembly. We chose to use the top wall plates to transfer the air barrier from the outside face of the wall assembly to the inside face of the wall assembly, where it could then be joined up to the air barrier on the ceiling. This involved ensuring that when the outside sheathing was installed onto these top plates, a ribbon of this joint and seam sealant was applied to the outside face of the top plate first before the plywood was adhered. This is detailed in this build photo taken earlier in construction. We used Prosoco R-guard fast flash at this location as a lot of movement was not expected. The sealant, as I explained, was applied to the outboard side of the plate prior to affixing plywood. Any sealant that squeezed out was trawled smooth with the cutoff from a caulking tube like the ones you see here. These can be made in any shape needed and are cheap. As our delta vent membrane extended past the outside surface of the top wall plates, we now have a continuous air barrier transferring through the wall plate to the inside surface. The gable walls required a little extra work as the top of the plates are well below the ceiling level. So we used a 2x4 and sealed it to the inside surface of the sheathing at the same plane as the slope of the ceiling, as you can see here. In this image you can see the blocking first being installed between the gable trusses, and then final sloped 2x4 being attached to the blocking, all pieces being sealed as we went. Our thermal barrier for the roof consisted of 18 inches of Rockwool's Comfort Bat mineral insulation. This was installed in 4 layers with staggered seams. If drywall, instead of OSB or plywood, was to be attached directly to the bottom side of the trusses, some of the thermal resistance would need to be sacrificed to allow that insulation to be pushed further into the bays so that it was flush with the bottom side of the truss and still maintain the required airspace of the top. This would be needed to prevent the insulation bowing the drywall after installation. With plywood or OSB attached, it was rigid enough to push the insulation up and compress it as required. An extra step was taken to fill in the webbing of the trusses with the Comfort Board IS from Rockwool to further reduce the thermal bridging, as you can see in this image. This image also shows the blocking and cross purlins used to create the cross-truss bay ventilation and provide the required 2.5 inches between the top surface of the insulation and the underside of the roof deck. The purplish hue is an antimicrobial that I applied to the underside of the sheathing surface to prevent fungi growth in the future, which is a very common occurrence in the Pacific Northwest. With the roof insulated, we were able to move on to the final step in our roof air barrier and installed an OSB subsealing that was installed with all of the seams sealed with R-Guard's joint and seam, as you can see here. It was sealed to the outside plates that we had earlier sealed the exterior plywood to. It was also sealed to the blocking and diagonal 2x4s that we installed at the ceiling plane. And then any seams and even screw holes were sealed to prevent air movement through the OSB assembly. At the other end of the assembly, the upper end, we were able to seal the OSB to the membrane that we had installed on the outside of the clerestory wall for the lower south roof, and for the north roof it was sealed to some plywood strips that were installed on the inboard face of the wall during construction that were then sealed to the top plates and the outside air barrier that wrapped around. These OSB sheets are also going to act as our vapor barrier because they are fairly vapor tight. They would sort of be a class 3 vapor barrier, I believe, which is all that's going to be required in this location. I may also give it an extra layer of protection on the ceilings with vapor barrier paint. I'll discuss that with my team and see what the recommendation is. But you can see here with the exterior membrane on the sheathing coming up to the top plates, the plates being sealed to that sheathing, the plates being sealed to the OSB, all the seams of the OSB being sealed. We have a continuous air barrier, and I am expecting a very low air tightness rating, ACH 50 number. I'm looking for 0.5 at ACH 50, so we'll see how we make out. Obviously, any penetrations through these plates and through the OSB needed to be sealed. And you can see that was done here, both on the top surface and the bottom surface. I also did the same thing where I had to pre-strip some network cables and low voltage cables up through there, and before I insulated on top of that plywood, they were sealed around the interfaces on the plywood, the penetrations on the plywood. For our waterproof roof surface, we installed a 2-ply modified SBS Torchon roofing from Suprema called Sopraline Flam 180. And as you can see, we also installed some raised curbs that will later house or support the photovoltaic cells that I'm going to be installing on this roof. The connection for the voltaic and possibly a wind generator in the future is going to be through these boxes that you see here. I also installed a permanent roof ladder that will allow easy access to the second upper roof that will allow for maintenance at that corner as the tree droppings build up. The only part of the roof assemblies that's not complete at this point is a cap plashing that will be installed over the top of the parapet walls. This will be done a little bit later once I've installed the fascia material, which will be the same architectural panels as I'm going to use on the feature walls at the front of the house, this being one of them here. We'll also have some natural light coming into the garage via these sun tunnels. The lids are on, but I still have to install the actual tunnel assembly inside. And all of our roofs drain to a central large diameter drain before that water's taken off into the storm sewer. The next component in our building enclosure was to install the subslab thermal, water, and air barriers. As you can see in this image, we installed 4 inches of Rockwell's Comfort Board IS below the slab. It had only just been approved for this application, and you can see all the mineral wool insulation lines up with the XPS that we installed around the interior footings at the very beginning of the build. You can also see the vapor and water barriers folded up out of the way, and they will, in a later image, you'll see that they have been sealed to the subslab membrane. On a side note, I will be testing 4 different insulation strategies for below slabs. On the far side here, I have EPS insulation, 4 inches of EPS insulation. I have 4 inches of XPS insulation. I have 4 inches of the mineral wool insulation, which I've installed throughout the rest of the dwelling. And then I believe this is 10 inches, and I'll put a note on the screen if that's not correct, of mineral insulation to simulate what happens or what Passive House recommends. These have multiple instruments. You can see that they go off to an instrument bundle on each bay. There is 2 sets of instruments per bay, and they are installed at the gravel layer, mid depth of the insulation, on top of the insulation underneath the vapor barrier, and then on top of the vapor barrier. And the reason that these are still open is that I have not detailed the insulation inserts that are going to go into these gaps and allow them to be taken out at a later time for testing at BCIT. And then I'll be pouring individual slabs on top of each of these openings that have anchors inside of them, and I'll have a jig that rolls over top of the I believe it's a 4x6 slab, and allow it to be raised and rolled out of the way to get access to the instrumentation and the test samples. Once we had our subslab insulation in place, the final step was to install the subslab membrane. which acts as an air barrier, soil gas barrier, water barrier, and vapor barrier. We used a product from W.R. Meadows called Perminator. It's a 15 mil membrane. As shown in this image, the membrane was sealed to the poly that we previously installed around the interior footing forms with Perminator tape. And then in this image, you'll see that the membrane was sealed to the exterior footing bags with a combination of membranes I had left over on site that were all appropriate for the task. I just didn't, I wanted to use up some old stock I had. All the penetrations, the plumbing penetrations, were sealed with foil face, and then the R-guard joint and seam, as you see in this photo. The foil face was used because the poly, the makeup of the membrane, the Perminator membrane, was something that the R-guard may not stick to long term, but the foil face stuck very well to it, and the R-guard sticks very well to the foil face. And then the last step prior to pouring the basement slab was to install a perimeter of XPS along the slab edges against the inside face of the foundation wall, and this prevents the thermal bridging that can occur at the slab edge, as you see in this image. With all the water, vapor, air barriers complete, we were then able to install the water shedding surface, i.e. the cladding around the home. This is basically complete. I've got some tiny trim work to do around some of the lower windows and doors, and I have some final staining to do. It requires 2 coats on the siding. I pre-stained it once on all 6 sides, and then an additional 2 coats need to be applied once it's been installed. They were back stapled to the furring strips with stainless staples to prevent the streaking that you see in these photos. And all in all, the system worked quite well. The installation of the siding was very time consuming. I mitered every single cut end. If it was a corner, they have mitered corners, and you can see that here. And then if it was an overlap, which you can see some of them up there, they were mitered so that you didn't have a butt joint, which doesn't look good, but it also would allow water entry. With them being mitered at a 30-degree angle, the likelihood of water ingress past those joints is very unlikely. One other thing that we may as well look at while we're here, part of my envelope design was to minimize thermal bridging wherever possible. So for our deck, the deck is actually hung from the wall with these hangers that you see here, and that allows us to only have 2 penetrations into the building envelope. And these basically, these outside beams just sit on the inside plates. And then there was a tri-beam that was installed 6 inches outboard of the sheathing that you see here, and that allowed the 6 inches of exterior sheathing to be continuous past the deck surface. Well, I hope this has been of interest to you. I have to admit that this hasn't been as easy a video process as I had hoped. One of the things that I noticed when I was checking the videos that I was creating as I went along here is that if I was wearing the camera, which is what I had hoped to be doing, that there was a lot of twisting back and forth of the image as I looked at different things, or as I tilted my head. For most of the last probably 10 minutes, I have been holding the camera in my hand, and that seems to provide a much better image. A friend of mine has a gimbal that he may not need, so I'm going to look at getting that from him. and hopefully that will then improve the quality even further. The final thing that I'll talk about on this video is the ventilation that we had for our roofing. So on our lower roofs, the lower and upper roofs all had the same continuous soffit venting strip that went around just the inside face of the soffit, or sorry, the inside face of the fascia. On the lower roofs, the upper end of the roof was vented through a continuous gap that was created between the insulation and the roof deck. And I'll show you the upper side of that in a sec. The upper side of that was the base of wall flashing, which had a screen, which I'll show you in a sec. On the upper roofs, obviously there wasn't an interaction with the second floor walls. On the upper roofs, the top end, and you might be able to see it from here, just had a continuation. You can go around the side here. Just had a continuation of that perimeter venting strip that went around. And as I was installing those strips, you can see that, I guess you can't see it here, but that basically, the black strip that you see, just continues all the way up on the top side. And I was installing the LED light strips that I have for my soffit lighting. I definitely could feel the hot air being pushed out of the upper end of the roof assemblies. It was very noticeable, a significant increase in temperature. Here you can see the base of wall flashing installed on the outside of the 6 inches of insulation, and the part that I showed you below comes up as a gap right here, and I'll try to show you underneath. You can see hopefully if this adjusts, let's see here, you can see a continuous strip of perforated stainless vent strip, and that allows the air to come up and over and escape from the lower roof assembly.
At the base of all walls, including the intersection with lower roofs and at all windowsills, we installed a cross-cavity membrane and flashing assembly to daylight any water that penetrated the rain screen cavity. The metal flashing was mounted to the outside surface of the insulation with long screws that reached through the insulation and into the wall sheathing. A foil face membrane was then adhered to the membrane over a tapered insulation package and then onto the up leg of the metal flashing. This prevented the thermal bridging that would otherwise occur if metal flashing was fastened directly to the sheathing. The Delta multiband tape has yet to be applied to the seam between the foil face and the Delta vent membrane in this photo. At the top of the wall assemblies, we needed to create a ventilation exit for the rain screen assembly. This would make the rain screen capillary break a ventilated and drained assembly and not just a drained assembly. It is important to terminate this vented rain screen before the attic space to prevent moisture-laden air from entering the attic space, where it can condense on cold surfaces in the winter and increase the humidity levels in the summer. We installed a continuous block to the bottom side of the top roof truss cord and then a siding baffle that pushed the air down and away from the soffit surface. We also ensured that the soffit venting was as far away from the rain screen vent as possible to ensure that the escaping air would mix thoroughly with ambient air before being drawn into the lower roof soffit vents. The perforated stainless steel screen visible in this photo prevents bugs and rodents from entering the rain screen cavity. Where the blocking did not sit tight against the insulation due to construction tolerances, we installed metal flashing to ensure the airflow could not bypass these areas. The underside of the blocking and the insulation were painted a dark brown to provide a finished look when viewed from below.
Well, that's it. Again, I will try to do better in the future with these videos and post them much more often. But for now, I bid you adieu, and thanks for visiting.